Или не купишь, или не получишь услугу. Или
Это во всех магазинах так?
это везде, где нет ценника, и где магазины без
Терминала без кассового
да.
аппарата?
Кстати, вот в Николая, в некоторых таких небольших лачугах, там такая штука работает. Попросить сразу дома.
Ну, мы обратили внимание, что это действительно разница с пунктами здесь, то есть за обед, там, если в Пунтагане иногда, ну, туристическая зона, ты там можешь заплатить на двоих 800, 600, до 1000 песо. То здесь, вот если ты пойдешь в какой-нибудь торговый центр, это будет совершенно другая сумма.
Намного меньше, конечно, потому что это остановка для бедных людей, и там как бы есть цена здесь, да? Да, конкретная цена. Но если ты говоришь, ты будешь платить где-то так.
Да, но так можно завести. Понятно, что в каких-то таких...
Это же там же в основном сапористы, здесь тоже, наверное, мало наверное, людей иностранцев.
Are you good to go?
Yeah.
Are you good to go?
Yeah.
All right.
Bueno, antes de empezar, si alguien quiere café, agua, se puede ir atrás para no interrumpir lo menos posible a Oleh cuando comenzamos. Pero nada, en el día de hoy, Oleh estuvo participando el sábado pasado en Santiago, en el Discord, y tuvimos una conversación ahí. I'm sorry, sí que es nice.
No worries.
Tuvimos una conversación y estaba interesado en compartir parte de lo que estuve impartiendo ya. Y nosotros dijimos, no, qué mejor oportunidad que eso, ese de ganar en Punta Cana. Y hicimos venir para la capital, literalmente nada más. Nada, él va a tratar de cubrir este tema el día de hoy. Nada, todo de él. Al final, cuando termine la charla, vamos a hacer un par de anuncios, pero vamos de nuevo al contenido.
Hello, amigos, and thank you for coming, and thank you for being patient because we have to wait for everyone. And first of all, thank you for your attention and thank you for coming to this Google developers group, Reactive. I don't know which one is what's the number of the meetup, but let us name first Reactive Google developers group meetup, at which we are going to talk about how to build Reactive Server engine using just everything from scratch and using just plain GDK. In order to save your time, in order to save time for everyone who is out of offline or online listening to this talk online, I want to start with a little bit of explanation for this talk and what benefit you will get afterwards. So this talk is for everyone who wants to learn about a little bit more about first. Like there is Neo second, but we are going to talk about Neo first because it's still up-to-date technology. We're going to talk a little bit about Project Reactor and how to apply Project Reactor in order to get better API around non-blocking I/O. And we are going to see how this reactive approach could be applied in order to build server-side engine. Does it make sense for you? Is it? I'm just curious. How many how many of you are using reactive programming nowadays? Just a few hands. Are you using RxJava or maybe Project Reactor? Okay. RxJS. Okay. So in general, everything will be pretty familiar for you because API is almost identical on the JS side as well as on the Java side, but we're going to talk about Java side because I'm a Java developer. Anyways, I will try to make things easier for you by explaining how you can benefit, for example, and start using Java nowadays. All right. Let me introduce myself. My name is Oleh. I work for Netify. I'm contributor to Project Reactor. This is one of the Reactive Streams libraries in Java world. And I'm contributor and committer to RSocket project, which is Reactive Streams and Reactive Programming as an application protocol, so you can achieve the same Reactive Streams from one service to another. But yeah, this is another topic. And I'm running a few conferences in Ukraine, so if you want to come to Kiev, to Ukraine, enjoy our cold weather, learn something new about Java and related technologies, I'm welcoming you. If you're curious, just let me know. I'm going to share with you some discounts. But this is off topic. Yeah, a little bit more marketing today. I wrote this book. So if you want to learn about reactive programming in Sprint 5, for example, just let me know. I'm going to share with you some PDFs with this book. So just let me know who curious and who want to learn about reactive programming in Sprint. All right. And finally, agenda. So first of all, we are going to start with understanding what we want to see under Reactive Server. What does it mean for us, and what we want to achieve here. Then we want to see why do we need that, because we have, in order to start doing something, we have to figure out why do we need that. And finally, we are going to implement that using Project Reactor and reactive technologies. Does it make sense? All good? So far, so good? All right, let's start. First of all, let's start with definition of Reactive Server. So what we want to achieve here. First of all, we want to have some server. This is clear. Then we want to make this server accept some incoming connection, because any server should accept some connection. We have to ensure that it's possible to accept any connection. But from this point, we want to add some more kind of useful logic, because any connection should be handled somehow. Any user should be able to connection. So we want to create some pipeline of data processing, because using imperative programming is easy, but sometimes it's really hard when we start talking about and working with some asynchronous data stream. And since connection and like TCP connection or whatever connection is basically a stream of data, it would be really useful to process everything in the same style, in the same functional, asynchronous, maybe reactive style, right? What we want to have afterwards. Afterwards, we want to have some more optimal data handling and connection handling. So what we want to have a pool of resources, kind of a pool of workers. In Java, it's a pool of threads. In any other language, it could be a pool of other processors. So basically, what we want to attach every connection to some specific worker, so it's handled by specific thread. It will simplify any data processing, because everything will be handled by the same worker, and it will make our life easier on the one hand, and on the other hand, it will make data processing more efficient, because we will share like pool of work, a pool of connections, or more connections between a few workers, which will going to handle everything, right? Does it make sense? Finally, in order to make our server reliable, in order to make our system, because we're building nowadays system, not just a plain application, because nowadays we have few microservices, we want to apply some more, we want to add some more reliability to our application in the way of applying back pressure. How many of you heard about back pressure before? Just one hand. So before we are going forward, I need to explain what is back pressure and why it's important. So now I'm going to show you a little bit of real life demo using these packages of coffee, like Java coffee, and I'm going to show you a simple game. So just imagine that you're building a system, right? In every system there is a client, like system that has networking in between. So in this kind of systems there is client which is sending data, and there is server, right? So once we start communication, first of all, the server has to be started up. And once, for example, I'm server and she's my wife, she is a client, she will start, like every client sends some data. So she is a client, I'm a server. Once I started, I'm going to say, okay, I'm ready to handle data, and she will start throwing these packages of coffee into my face. This is the task of every client, right? So every client should send data as fast as possible. For her, it could be a little bit of fun, throwing packages into my face. So once we have this communication, I have only 2 hands to handle all of those packages, right? Every system has some capacity. So I will be trying to handle all of these packages as fast as possible. Her task is to send and to throw these packages as fast as possible. So let's try to apply this game, and I'm ready. Please start throwing packages as fast as possible. And as you can see, I have only 2 hands. And those packages could be much more like we have much more packages. Like there is only 4, but in fact it could be 1,000, and your client could send 1,000 like of data of logical elements into your server, and sometimes it's okay to drop some of those messages because you have some capacity. Every system has a limited capacity, so at some point in time it will start dropping messages, dropping, for example, some logical elements, but sometimes it's unacceptable to drop packages. And in that case, we would have to apply some retry logic. Afterwards, we would have to apply some timeouts, circuit breakers, etc., which will make our life harder, right? This was an example of absence of backpressure. This was a kind of ordinary communication between client and server. But now, just imagine that in addition to saying that I'm ready, I can specify how many packages I'm ready to handle, because I know that I have only 2 hands, right? Not more. And you know and how much memory your server has. So you know what amount of messages it is able to handle. So just imagine that along with saying that I'm ready, I'm going to specify how many elements I'm ready to handle. It should simplify my life. So let's see. Let's try the same communication. You should throw as fast as possible. I'm ready, but I'm ready to handle only 2 packages, right? Because I have 2 to hand. So please throw 1, 2. It's the same speed, but now I'm able to handle it. So I can put it somewhere. I can put some coffee. I can do whatever stuff I need before I request for a few more. But let's imagine that I process them, and now I'm ready to handle another few. Just 2. Send me another 2. 1, 2. And here we go. In this way, I can accept messages almost with the same speed. Of course, it will have some delay. But just imagine that now server can control how many messages it is able to accept. And then based on this number, client can balance the number of messages between other servers. And in this way, we will preserve some stability in the system, right? So this way is called backpressure or flow control. And we are going how it will reflect in the future, like further in specific technologies, reactive technologies. But in general, it's clear what is backpressure and why it's important. So we want to have in our system backpressure control, and here it could be exposed over some client-side backpressure control. So client will be able to say how many messages it is able to process, or for example, it could be driven by output. So based on the other server or the ability or the kind of availability of the connection, we can figure out whether we can process some data or can't. And afterwards, once we are ready to process, we will read some data from the connection, we'll process it over the logic and send it back. Right? That's what we want to achieve. That. Does it make sense? Yeah. All right, that's good. So from the code perspective, this mechanism could look like this. So basically, it's pretty functional style of writing code, for example. At the beginning, we can create some server. We can say, okay, we want to run this server on localhost 8080. This is most common thing that we want to do this, for example, on the server side. Then we want to define some handler for incoming connections, because we want to say, okay, now I want to apply some business logic. So it could be handle method that applies, that get some or accept some connection supplier. And based on this connection, we want to have some 2 methods, 2 basic methods. First one is receive, which could, for example, give me some functional API, some Reactive Streams API, using which we'll be able to build some logic processing, right? And afterwards, we want to just send this stream back using the same connection. So does it make sense? It's really plain and easy API with some functional data, like using some functional data processing style. And finally, yeah, we want to attach that to specific, of course, worker. And afterwards, once we build our logic, we want to start our server and block, for example, the main thread in order to make our application continuously working, right? That's what we want to have. We want to have in our server side, reactive server side. But now we have to ask the question, why do we need that? Why do we need this reactive server engine, this functional reactive style of data processing? And in order to understand why do we need that, we have to figure out what's wrong with with the things, with technologies that we have already applied nowadays, right? What's wrong basically with blocking I/O? What's wrong with why do we need non-blocking I/O? In order to understand that, we have to take a look at the blocking one, right? So let's take a look at the small demo in order to figure out what's wrong with that. So here I have just a plain main method. Can you recognize what's going on there? Do I need to increase maybe font a little bit? So let me increase it a little. So for example, 24. Is it better? Okay. So let it be 24. And yeah, this is just a plain main method in order to start my application. And now I'm going to quickly add some boilerplate code, which basically creates a block-in I/O server. So this is create a server socket on the port 8080. And now using kind of the most common way to read some data from this server to accept connection, I'm saying that I want to accept some incoming connection. This guy will block my thread until I got new connection. So once I got new socket, I'm start reading some data from this socket. I'm gonna buffer every line of data, and then what I'm gonna do, I will for every line from this socket, I'm gonna translate or add some echo message to this guy and send the same message back. So this is basically a socket echo server. All right, so let me run it, and you will see how it works. All right, so what's wrong with that? Come on, buddy. Okay, I have to specify a module. Not this one, but this. Now it should work. All right, it started. So in order to figure out whether it works or not, I'm going to use telnet. I'm going to connect to my server. Can you recognize what's going on there? Okay, that's good. Localhost 8080, and I'm connected. So in order to figure out whether it works, I'm going to say hello GDG Santo Domingo. And here we go. We got echo, hello GDG Santo Domingo. It works. So if you're going to write more messages, you will see that every of those will be echoed back. It works. It's pretty good. So in order to figure out what's wrong with that, we have to open a little bit more connections. And let's try to not kill Java, because yeah, the previous one was kill Java, telnet, localhost 8080, and now it doesn't work. Before it works. So if I'm gonna open this one, it works. This one doesn't work. So if I'm gonna open another one, not this one, telnet local, okay, local. It still won't be working, right? So let's take a look at the code and let's try to figure out what's wrong with that. Do you see any problems here? Why it doesn't work? Why I can open only one connection and not more?
I think you need some thread management, like thread connection, and external object that manage this thread.
Right. So basically, we need some multi-threading. For now, blocking I/O, it's literally blocking. So once you accepted one connection, it will block your thread. It will basically block the thread which is accepting other connection. So other connection will be blocked until this socket is working. So if I'm gonna, for example, close this one, yeah, I'm closing this guy, you will see that this one got their answers, and now this one works, but not this one. So basically, the problem is the blocking I/O is blocking. It will block the thread. And the simplest solution here is to apply or to add a few more threads in order to process more connections, right? Does it make sense? Yeah. So let's do the following. Let's add, not this one. Let's add the thread pool. So this is kind of the simplest way to create a thread pool in Java. So I'm going to use the same number of threads as my machine kind of has a core. And this will be around, for example, 16 cores, but let's just for simplicity create a thread pool of 4 connections, right? Now, in order to make it multi-threaded, let's apply some logic which allows me to handle all of those connections on the separate threads. And now, once I accepted my socket, I'm going to execute data reading on this socket on the separate thread, right? Easy. So let's restart it, and let's take a look whether it will solve our problem. So it's restarted. Now let me connect to my server. It works. Let me try to do that. Okay, now like this. It works. Amazing. Another one. It works. And another one. It still works. But what if I open 5 connections? It doesn't work again. So the same problem. We are out of available threads because the same block in IO. So maybe we have to create a non-block kind of cached thread pool or unbounded thread pool, which allows us to handle every new connection on a separate thread, right? Does it make sense? So it's easy to, in Java, it's really easy to create cached thread pool, which will basically create a new thread for every new connection. So it should solve our problem. And now we will have unbounded pool of connections, and we will be able to connect as many clients as we need. So let's try to again. It works. It works. And it works. And it works. Amazing, brilliant. Of course, I can open as many tabs as I can, but it won't be productive. So in order to figure out whether it's an acceptable way to process data, I created a small test application, call it Dosser. So this application is basically the same socket client, which creates 10,000 of socket connection. And after that, using all of those connections, I'm gonna send some hello DOS attack message, and you'll read it back, right? This is a really simple way to check whether my server is capable to handle 10,000 of connection. Have you ever heard before about 10K problem? Yeah? So let me do a little bit more intro. So if you're going to Google taken problem, this is basically a problem of handling 10K connection at the same time by one server, by one machine. This question was asked by one scientist, computer scientist, in, I guess, 1999, almost 20 years ago. Yeah, 20 years ago. And he tried to solve using the same hardware, the same technologies. He was trying to handle 10,000 of clients on one machine. So let's do the same. Let's try whether blocking IO is capable to handle to solve 10K problem. Of course, nowadays we should handle 100 of case of connection at one machine, but let's try to solve this problem using blocking IO. Now this, not a JetBrains help. So now I'm gonna start displaying up. Okay, again, the same. And we will see whether my blocking IO server is capable to handle. Yeah, it's working pretty good. Almost 7, 8, okay, 8,200, and it stopped. Do you have any idea why it stopped? Huh?
By the number of selectors that the process has, we kind of limitation of the
Not my application. Like this Java processor on my machine has around 10,024 or 84 or 200 and something sockets for this processor. So I'm capable to open a little bit more than 10,000 of simultaneous connections. So the problem is not that, but the problem is like in memory. Right, and if you're going to look at this memory, you will see out of memory, because in fact, every thread in Java, on average, like for example, on Mac and on Linux, takes 1 megabyte of memory for its stack, and a little bit more for for some additional stuff and for some internal buffers, etc. So in general, every thread takes 1 megabyte of memory in order to do his stuff, and it's really expensive. And this is real problem of blocking I/O and blocking servers built around blocking I/O, because without having too much memory, it's almost impossible to handle this many connections. And of course, once we start creating 10,000 of threads, we will observe we will be faced with another problem, which is contention and concurrency between them on some resources, because we have only 4 processors, or for example, only 8 processors on our machine. And all of those processors will be shared between all of those threads. And this is a problem. So it will be too slow afterwards, and it will make too much pain for us. So now it's clear that blocking is not the right way, because we have a few problems related to blocking. First of all, it's inefficient resource usage, too much memory for stack. And of course, we can decrease it, we can play with it, but this is not a solution. It increases latency because too much contention between all of them. And of course, it's easy to DOS this application because, again, the same problem of blocking threads and contention between them. However, it's worth to say that working with imperative programming, with blocking programming, is as easy as pie. So it's really simple to build such server, right? It's not a complex task. However, it's clear that we need something else. For example, we need to take a look maybe at non-blocking I/O. If you're going, how many of you heard about non-blocking, about NEO? Okay, great. For those who have never heard about non-blocking way of doing doing interaction on the server side, I'm going to quickly introduce what is the important points you have to know about NEO and NEO first in the Java. First of all, in the Java side, there is the main server representation is server socket channel. And server socket channel is basically a non-blocking server. Now, in order to handle all of these non-blocking events, we have to introduce another part of non-blocking I/O, which is selector. And in order to start listening to some updates to some incoming connection, we have to register selector into the server socket channel. For example, in order to listen to new connections, we have to register our socket channel using selection key with operation accept. So this is the first step. Once we get a new connection, once somebody connected to our server, our selector will send kind of notification to us. So afterwards, we will be able to process this new socket channel that connected to our server. But then there is a few more complex steps afterwards. In order to start listening to some incoming data from this socket channel, we have to register our selector, the same selector, into socket channel. This is another place where we have to register our selector. Do you see that? Okay, we registered our selector with operation read. And for example, at some point in time, we received some data, some bytes from the client side. So selector will notify us, selector. It will only send socket kind of selection key. And now we don't have those data. We don't have those data. We got only notification, which doesn't have anything in it. This is only notification. And now, in order to read this data, we have to go to socket channel and read bytes from socket channel in some non-blocking way. We have to process them, of course. And now the task is how to write them back. So, for example, in blocking I/O, we have to just send everything to write method. In non-blocking I/O, it is the same. It uses the same way. It uses the same technique. But in some cases, it will write everything. But in the worst case, it will write only part of our buffer. Because again, we are in non-blocking world right now. And just imagine that, for example, connection is not available or our client is not available to handle all this data. So we will write only part of them. And now we have to store the rest of them somewhere. We have to register and listen to another event, kind of operation write. And once we receive this operation write, which basically says that our connection is capable to receive more data in it, we will be able to send the rest of the things, the rest of the buffer to the connection. And in case it flashed, we are good. Otherwise, we would have to put it back somewhere. and wait for another operation write notification. So this is how basically non-blocking works. It provides the same imperative API as we're going to see on the next slide. It provides the same imperative API. What we have to do is basically we have to, for example, start our server, open the socket on specific port, say that this is basically non-blocking server, and afterwards we will be able to process the rest of the thing. For example, using the same imperative way, because this is the same Java, but with some non-blocking technique to process data. Yeah, we would have to open selector. This is basically a selector in order to listen, and afterwards we will be able to accept some incoming connections. So let's take a look at logic related to connection acceptance, for example. This is what we can write inside inside our while true loop, which is basically we'll be looping and checking whether there is no new events, whether there is new events in we will get this flag acceptable, and we will be able to process incoming socket channel in this way. For example, we'll be able to accept this connection. We would have to configure, and we would have to say that this connection is non-blocking as well, along with the server one. And then we would have to put this connection somewhere, because we would need to work with this data, with this channel afterwards. And yeah, this is another challenge. So we would have to put this connection in order to process it. And we would have to create a storage for all the data, etc., and so forth and so on. And the next stage, we would have, for example, we would need to process data from this connection. So we would have to add an additional if-else section in which we have to check. We have to wait for some readable notification or for some selection key with flag readable. And in this case, you would have to write almost the same logic. We will have to allocate some byte buffer for incoming data. We would have to read it. And the main challenge afterwards is how to process all of those data. Because now we just read this byte buff. So either we would have to store it somewhere, but now the question how to send it to client, right? Because client have to handle this data. And this is unclear point of this data flow. Because we would either have to have some data handler or some additional logic, and it becomes really hard. And in order to make it in order to build it in the same non-blocking way, would require to apply too many techniques, which would make this code much more uglier. Finally, we would have to write this data somewhere, and here is basically logic related to data writing. So we would have to read all of those bytes read from the network, processed somehow, and now we would have to use another while loop in order to check whether we are capable to write everything to the connection until it's while it's ready. Otherwise, we would have to use another selection key and wait for operation write, or in case we wrote everything, we would have to switch our selection our socket channel to waiting for operation reads. Does it make sense? Yeah, it's kind of complex.
What we're just trying to explain is that pretty much that's how Node.js works. Like human things until it's ready for.
Is kind of built as a pipeline of data processing. So from my point of view, in Node.js, it's a little bit simpler because you don't have to work with this lower level stuff. In Java, it's way complex. And
you're working just with one thread, right?
Yes, this is only one thread application. We are not talking about multi.
So right now it's like just one thread, one loop, right?
Yes.
So the loop is stuck completely. You're creating that step, right?
So yeah, a few more explanation points. Why it's not blocking? Yeah, this is. Let's go back to this. Now this one. Let me.
Because even if it is like emitting all those events, all those operations, there is one part in the code that shows that it's basically taking all the data from the, I think it's moving from the read channel to a queue.
Right.
And I believe probably if it's, I don't know, 1 megabyte of data, it's like it's stuck right there, right?
Yes and no. So if we are going to get to receive really big message, we are going to read this message until something. Yes, until we read everything from this channel, or we can create another logic. Again, this is another challenge, how to apply some business logic on this data processing flow. And yeah, we're going to back to this when we start talking about reactive programming. But in general, this will block one thread until we get a new event. But again, this is kind of non-blocking because we don't have to block our thread when there is no available data in this socket channel. So once we read some portion of data, we can send for some data processing. We can kind of apply some business logic on top of that, and afterwards we can try to switch to move our selector to another state. For example, waiting for write events. And once we enqueue with write event to be handled, we can process another socket. So everything will be processed by one thread, but since this is a non-blocking IO, it won't block any thread. It will just block a thread until new events. This is only one blocking point. That's why everything in while true, because we would have to check kind of to block thread, check whether there is new events. If there is nothing new, we would block our thread. Once new event appears, we will unblock this thread, do some job, do some work, for example, and queue something in the queue, wait for another event, and loop again until another event. So that's how it will work. And this server will be capable to process much more. I'm going to show you. So let me quickly switch to the main, to the summary of what we have seen, because this is important. And we have to talk where is the complexity in there. And basically, the complexity is everywhere. And Neo API is basically really complex and really challenging in general, right? So as you have seen, there is too many points of failure. And it's unclear how to process data and so forth and so on. There is absolutely no relation between selector, because selector just sending notifications with selector keys. And there is no data in these selector keys. This is just a notification. In order to process some data from your socket channel, you would need to get this socket channel from the map. You would need to read this data in some other way using absolutely unrelated API to the selector, and then process it somewhere else. And this is a main problem and main complexity. And yeah, this is absolutely non-blocking operation. So you would have to expect that at some point in time, only part of your byte buffer will be written, right? Or you will read 0 from your socket channel, so you would have to skip this byte buffer, created byte buffer, and so forth and so on. Too much problems. And we are not talking about, for example, back pressure, because it's unclear how to apply back pressure there. Plus, how to handle all of those data in multi-threaded environment, because we want to process everything really efficient, right? Too much questions that we have to solve, and this is too hard. It looks like this. You are Hormer, which are working in some unclear reactor factory and some absolutely unclear API and really complex API. And I have a good seed from one well-known person. This is Venkat Subramanian. Have you ever heard about him? All right, he is really popular in Java world for sure. And he says, don't fall from complexity. You don't have to be afraid about complexity. What you have to do with complexity, you have to run from it. Run from complexity. Don't try to solve something in really complex way, because it's absolutely a sign that you're doing something wrong. So now it's clear that we have to run to somewhere. And one of the safe harbor is Reactive Streams, because basically Reactive Streams is asynchronous non-blocking streams. It's a paradigm of processing asynchronous non-blocking stream of data, which is basically fits to what we have in our socket channels, because socket channels is TCP connection or UDP, doesn't matter. It's a stream of bytes. And now we can process the same stream of bytes with the same paradigm. This is pretty cool. In turn, it naturally fits. So it naturally fits to non-blocking I/O, and it has built-in back pressure in it. So this is amazing. If you're going to look at Reactive Stream API, you will see publisher. This is one of the interfaces which basically represent the producer side. There is a subscriber which have to be given to a publisher, and basically subscriber has 4 methods like onSubscribe, which is data exchange between publisher and subscriber. There is a next, which basically allows you to handle some incoming byte buffers, for example. There is onError channel, which will send terminal error in case of something, and there is onComplete in case your connection is closed, and you will be able to process it as well and complete your business logic, for example. And finally, there is a subscription, which is the most important part of Reactive Streams. And subscription, as you can see, has this magic method, which allows you to say how many elements you're ready to process at this point in time. This is basically method request. Yep, this is simple. So if you're going to put everything on the one picture, you will see that in order to start communication, subscriber have to subscribe to publishers, and publisher will give a subscription. And afterwards, you will be able to communicate with subscription, request for some data, and receive some data back over on next method. This is pretty easy. The same paradigm which fits pretty well into the same socket channel data processing. Of course, this is just an API. This is just a set of interfaces, I would say a specification for Reactive Streams data processing. But apart of this specification, we would need some library which simplify our life by providing some useful operators. So this library is called Project Reactor. This is one of the available libraries. Basically, for those who work with RX technologies, you will see that API is pretty similar because Project Reactor was built with some Ion RX Java API and Reactive extensions. So basically, Project Reactor is a superset library on top of Reactive Streams. It provides extensive set of operators like map, filter, etc. And it provides a set of operators which simplify your life with multi-threading and multi-threaded data processing. So what you have to need to know about Project Reactor is that this Project Reactor, you will be able to build the code something like this, right? Easy. In turn, there is 2 reactive types in Project Reactor. The first one is mono. Mono allows you to process 0 or 1 element. This is kind of a promise in JavaScript, or for Java developers is completable feature, kind of completable feature, which allows you to process only 1 element. On the other hand, there is another type, call it flux. And basically, flux allows you to process stream of data, infinitive stream of data, and we are going to use flux in many places, right? Does it make sense? Yeah. Great. So all of those reactive types extends publisher, which says that this library is built on top of Reactive Streams, and it has back pressure built in. Cool. All right. Let's try to code a little bit, and now what we are going to do. We will take the same non-blocking API, and we are going to build kind of reactive non-blocking API using Project Reactor. We are going to see how it simplifies our life. So that's what we are going to do right now. I'm going to switch to my slides. Here we go. And now, instead of this blocking server, I'm going to show you how you can implement the same using Reactive API. So here we go. The same data processing logic. Of course, we don't have any implementation so far. This is just a set of interfaces that I have shown you at the very beginning. But basically, the same task could be solved in a much simpler way. Do you see it? Using this Reactive API, we can receive byte buffers. We can send them back. And using this Reactive API, we can do lots of useful things. We can log everything. We can publish our data processing on another thread, and so forth and so on. So this will simplify our lives, and it will give much better user experience afterwards. All right. Now we have to take a look at the internals, and we have to implement, of course, something inside our Reactive Server engine. So here I have a few interfaces. So basically, this is a connection interface, that what you have seen at the very beginning. This interface gives to the user a connection which has a message received, which returns a flux of byte buffers, a stream of byte buffers. And this guy allows you to accept any stream. It could be RxJava Flowable, it could be Reactor, it could be whatever Reactive Streams basic library, for example, Akka Streams. So this API allows you to send any stream of data to outbound connection. And of course, everything is synchronous. So in this case, in order to wait for completion of your stream, it returns mono, which we are going to use inside our server, inside our server engine. All right, here we have some default connection implementation, which basically just a skeleton for our upcoming implementation. And here we have the same skeleton for our Reactive Server interface as well, which basically has one method in order to create our server, handle data, and start. Easy. So let's try to implement something. And now, in order to start, we have to implement some business logic here. Basically, we have to return some asynchronous data startup. So everything here should be started in a synchronous way. One of the options is to use, for example, Mono. Mono provides you a few static methods which allows you to create, for example, to run your runnable operation once somebody is subscribed. Another option is, for example, to use from callable and so forth and so on. But in this case, we want to use some API from Flux, because basically what we want to achieve, we want to, for example, apply some user handler on our connection. And this handler, as you remember, I'm going to show you, returns mono. So we want to collect all the mono. And in case of server kind of shutting down, or in case we are going to shut down our server, we have to cancel and stop all of these monos and cancel all of those kind of related to those monos business logic. So that's why we are going to use, in this case, we are going to use some Flux API. It's basically Flux push, which gives me a sync. So sync allows me to send any data into it. So it's basically, it has method next, which allows me to send anything inside into my downstream. So it's basically a way to supply some data to my stream. Then we're going to create some core business logic. I'm going to use some templates in order to save our time. But here I created basically the same code as you have seen on the slides. So this code related to non-blocking I/O. So it creates a socket channel. It makes it non-blocking. It opens selector. Do you remember that part? So it opens selector, and it registers this selector into server socket channel with selection key operation set. So we have started listening to upcoming connection, to every upcoming connection. Here, in addition, I'm using some Reactive API, some API provided by Project Reactor, which allows me to listen, for example, to cancellation, because user can say, okay, I don't want to listen, I don't want to wait for all connection. I want to accept only a few of them, and afterwards I want to stop my server. So in order to stop my server, I need to listen to the cancellation signal, and this is basically the way. And one of the options to react is this symbol. Let me replace it with some lambda. As you can see, once somebody called cancel or stop our server, I'm going to close this real server socket channel here. So this is just some infrastructure logic, and here we have our while true loop. Why not while true? Again, this is important point because somebody can cancel our server, so we have to loop only until the point of cancellation, not just until the end of time or stopping of Java process, but until the cancellation of our mono. This is the main reason to have Flux push, because, for example, from Runnable does not provide us with such API. So afterwards, we start selecting new events here, and here the same logic as before. So this is if-else logic which we have seen before. This is the initial part. This is just the beginning. So now we have to somehow start accepting new connections. So here is our socket channel. So we have somehow to process the socket channel. In order to do that, we have to take a look at our default connection. And at this point, we have to provide our business logic, because we don't want to write everything in one class, because it would make our application and our business logic too huge. We want to separate everything into separate kind of logical pieces of code. So we want to put everything related to stream and channel processing, data draining and sending into separate class, right? Does it make sense? Great. So here we need, first of all, we need some socket channel in order to handle our data. We need, of course, some way of notifications for another selection keys, right? Because along with selection keys related to new connections, we have to listen to selection keys related to unreadable selection keys. So it's notification about new data in specific channel. And this is notification that this specific channel is capable for handling some data back, right? So we need to create some way of this part. So this part should somehow notify this guy about these events. So one of the options is to use the same paradigm as before. Why we are not going to use the same paradigm? For example, what if we have the same way of data kind of processing, but in this case we are going to listen to a stream of not secret key but selection keys, right? So in this stream of selection keys, will send us a new event, and we'll call new on next every time we got a new event here, right? Does it make sense? Are you with me? So far, so good. Any questions related to that? So just imagine that there is a way to send this selection keys that we received here to this guy. So basically, what we expect from our reactive server, we expect a flux of these events. And we expect, like, this is, for example, read selection key, and we expect the same stream of write selection key. So afterwards, we will be able to listen to both of them in order to figure out what to do, right? So let me quickly put, again, the same template as before. Connection definition. So basically, this is the same things that we're going to use afterwards, and it provides a default constructor for that, which provides me with socket channel with some initial selection key from which I will be capable to read some initial data, and those stream of read notification and write notification on read selection key and write selection key, right? So now we have somehow to start our logic, because as you can remember, let me go quickly back to the slides. In order to start this data processing, you would need to let me show you. Yeah, you would need to register the same selector, this selection key operation read, right? That's what we need to do. So here we have our API. Now the question, where to put this logic? Yeah, in receive. So it's clear that we have to use selection key, current selection key, and we have to say, okay, we are interested in selection key operation read. But now the following: are we ready to handle those data? Because we identified that we are ready to read some data from the channel, but we haven't created any data pipeline yet, right? Do you see anything? We just, for example, let's just create a placeholder. We don't know at which point this stream will be subscribed, right? Do you know at which point? It could be any business logic. It could be data sending from for example, from the server side to another server using HTTP client or another TCP client, which is using the same Reactive Stream API, and we don't know at which point this stream will be subscribed, or subscription could be delayed. So we could start listening to upcoming data too early, right? And this could be a problem because we will receive some unwanted notifications and so forth and so on, and we will overwhelm ourselves. So maybe we need to start listening to operation reads only when we receive a subscription, when someone subscribed to our stream. Does it make sense? Yeah, so we have to listen to subscribe event. So since we have the source of read notification inside in this read notifier flux, maybe we would have to use some API from Project Reactor, and basically Project Reactor provides us with this API. We can use doOnSubscribe. There is doOnSubscribe method, which provides us with subscription. This method will be handled only and only when we got a new subscriber to our stream. So this is basically a place when we have to start being interested in this operation suite, right? Does it make sense? All right. So let me quickly put again a placeholder, because I have a placeholder for everything. And let me quickly build, really quickly, the data processing logic. So what we want to have here, we want to implement this business logic of using selector. We want to say, okay, we are interested, our socket channel is interested in this operation read, and we want to use the same selector as before. We want to use the same while true loop. You don't want to create another selector for handling. We don't want to create another while true loop because it will just overwhelm everything. We want to use the same thread, the same business logic, the same selector, which has already listened to some an operation set, and we want to say, okay, buddy, please help us a little bit. Please listen to operation reads for this socket channel. So that's why we are using the same selector, because the same selector will be attached to selection key. And we are going to register the same selector with operation read in order to make it, to start listening to read updates, to read notifications. So far, so good. Any questions? Yeah, it's hard part of business logic, of our server-side engine. So if you have any questions, please interrupt me and ask. All right. Afterwards, on every new selection key that we received from selector, we want to update our current selector key because we have to keep it up to date. There is another problem with non-blocking I/O. And once we received our first selection key related to operation read, we want to say, okay, I know that you notified me about read operation, so now don't listen to any other operations, because if we are not going to use that, we will observe that while true loop will just, on every second, on every loop, will just send me on read notification until I read this here. So here is my business logic on read. And until I read something from this socket channel, my selector will be throwing this on operation read selection key without any interruption. It will just burn our CPU to the higher level, and this is not good for us. So once we receive this on operation read, we want to say, okay, just wait for operation connect, which is basically has already happened, and we will start reading some data. So now the next challenge. We don't know how many data there is, or how many bytes there is in this socket channel, right? We don't know how much data our client has sent. So what we have to create another flux which will drain data from this socket channel until we drain everything, right? And in order to drain this data in synchronous way, in imperative way, there is flux generate. So flux generate will be handled every time subscriber requested data. This is another point, but we are going to run the same logic. We are going to use the same selection key, and we are going to use like the same notification until we read all of those data from our channel. So we create here a byte buffer. We allocate some memory for our bytes, and once we read something, it's important to read something. Once we read something, we are going to send this buffer to our this buffer to our flux. Otherwise, if there is no data in our socket channel so far, we have to say, okay, this stream, this session of draining the socket channel completed. I have to send a complete notification, and now I have to say, okay, now I'm interested again in operation read, right? Does it make sense? Okay, great. And this is basically a receiver part of the logic. So we are going to send this stream to our client with our connection. So the client will be able to call this receive method and build some business logic on top of that. On the other hand, we somehow have to process outgoing stream, because once client received everything, he has to send something back, right? So we have to process this data stream pipeline on the other hand, on the send method. And here we basically have to call subscribe method We have to call subscribe method. We have to create subscriber, because we need to build this logic related to data consumption, right? Here we have to say, okay, request some data, and now we have to store the subscription somewhere, and in general it looks really ugly. And if we are going to read some notifications from ID, it will say that please don't create subscriber yourself, as well as don't create publisher yourself, because this is a non-trivial task. And in order to avoid any mistakes, we're going to use something built into Reactor again. For example, Reactor provides us, first of all, we can easily say we want to wrap any stream into Flux. So that's easy. Just use Flux from. Come on. Use Flux from, and you can easily wrap any publisher not related to Project Reactor. And afterwards, you will get all of those built-in operators and methods. And for example, you will be able to use lambdas instead of creating subscriber interface. On the other hand, we have to listen to all events, including on next, on error, on complete. There is some built-in base subscriber, which allows us to handle only methods, only signals we really need. So this is other way to listen to create a subscriber and to listen to and subscribe to a stream of data. So another problem here, a few more problems, is that for every connection we will create an object, a stream, another stream, and it could be too much logic, too much object for our environment. And in turn, do we want to write this kind of code? It looks really ugly, right? Creating some anonymous class inside the class, it makes our logic unclear. So instead of creating an anonymous class, why we can't just simply extend our existing default connection from base subscriber? Because we can merge both of those classes, because we want to have this logic inside of one kind of class. So we can easily extend this guy, and we can subscribe the stream on ourselves. And this will be golden. This will simplify our life to the maximum point. So let's do like this. And now instead of creating anonymous classes, we can easily override, for example, we can hook on next event, and that's all we have to do, right? In addition, we have to hook to, of course, we have to hook to unsubscribe, because we have to make the first request, because in order to start data consumption, we have to request for some data. This is important to say that we are ready to receive something. This is the first request. And yeah, we're going to look what happened afterwards with that. And here we have to write, of course, some logic related to some writes. We have to, of course, here we receive some byte buffers, and we have to write this byte buffer into our socket channel back. So what we have to do here, first of all, what could happen, there is a few corner cases here. We can receive result -1, and basically -1 means that if you're going to look at the documentation, -1 means that something went wrong, our connection is closed, so we don't have to continue data processing. And basically, if we don't have to continue anything, we have to cancel from the stream. We have to notify our business logic that something went wrong. We want to cancel our subscription. On the other hand, we have to ensure that we wrote everything from our byte buffer. Because do you remember this point because related to non-blocking IO, that it's possible that we gonna write only part of our byte buffer, because yeah, connection is has some capacity, of course. We are using a TCP window in order to send our data. So our TCP or our receiver, for example, won't be able to handle some more data. So we are going to write only part of those byte buffer. And we have to check that there is no data inside byte buffer. In case there is no data, we are going to request for another byte buffer. Otherwise, for example, if there is some data inside byte buffer, which means that we wasn't able to write everything, we have to put this byte buffer somewhere. And one of the options is to put, for example, inside the same connection. For example, we can create a queue of those byte buffers. It doesn't matter. Or we can create a placeholder for 1 byte buffer, just for simplicity. So now we have to somehow be notified about the ability to write more data to socket channel, right? And we have this stream of write notifications. So we have to build the same pipeline somewhere. One of the places where we can do that is here. So we can say, okay, we want to subscribe to write notifications. So I'm going to use, again, some placeholders. And I'm going to create the same, almost the same pipeline around write notifiers, which is basically we'll listen to selection keys. And once we receive new selection key, we are going to put the same selection, the state, like we are going to move our state of socket channel to operation connect, because we will be overwhelmed of selection keys with operation write. And in order to avoid that, we have to say that we are interested in another event and execute the same hook on next, which basically executes the same business logic with currently stored byte buffer. Does it make sense? Yeah, a little bit complex, but just bear with me. Here, yeah. All right, any questions so far? Okay, there is no question. This is basically the whole logic that we have to write. On the one hand, it's a little bit complex because this is the same NEO. On the other hand, the general data draining, data listening, notification listening is much simpler because we are using Reactive API and streams as paradigm for data processing, which basically makes our life much simpler. So what we have to do, we have to do everything asynchronous again. So here we have to use from runnable, of course, and we have to subscribe to our stream only and only when our server said us that, yeah, we are ready to proceed with this connection. So this is one point. On the other hand, this class extends connection, and connection extends closable, which means that our connection should be closed, should handle close events, or should clean up resource afterwards. So we have to put some cleanup logic here. So let me put it there. And the cleanup's basically just disposing of this subscriber and canceling the stream. That's what we basically want to do there. All right. Finally, in order to make this business logic working, we have to implement those guys. We have a connection. So we are capable right now to create a default connection here. We are capable to supply selection key because this is selection socket channel here. Yeah, this is basically a socket channel. Yep, do you see it? Socket channel received from the server side. So we want to provide the socket channel, and now we have to supply initial selection key. That's easy. We have it here. Where is it? Yeah, the key. We want to supply a key. And now the question where we can get these fluxes. So yeah, our API requires us to provide a flux of selection keys, which is basically selection keys which appeared here. And we have to provide another flux of selection keys taken from there. So the question is how to do that. Reactor, again, provides us with really simple way. There is a processor in Reactive API. So basically, if you're going to look at the processor is a combination of subscriber and publisher. Subscriber allows you to call method on next, and publisher allows you to build a pipeline of data processing, right? So this combination allows you to supply manually new data to your stream. So let me show you. For example, if you're going to create a processor, not here, not this one. I have to delete this guy. Yeah, the processor. Let's make it like this. Byte buffer and byte buffer. So we want to have a processor which accept byte buffer and supply to downstream byte buffer. And now we will be able to call on our processor on next and supply manually data. So this is one of the options how we can create a flux which will be supplied to somewhere else and gives the data to this flux manually. So in Reactor API, there is unicast processor, which combination of buffer. So we can, like, there is a high chance that we can send a little bit more, but those data will be buffered until subscriber requests for this notification. And we are going to use unicast processor here. So now let me cheat a little bit again. And now let me create some, let me put some another placeholder. And yep, process notifications. So basically what we have here, we create two unicast processor, those two processors. We say that we create some queue for our data, and we put both of those processors inside our hash map, because in any ways we have to store our connection somewhere, because again, this is just a loop. And based on this key, we have to figure out to which selection, to which socket channel this key relates. And we have to associate selection key and socket channel with some some processors. So we are going to put everything into hash map. And now here we are going to use this hash map in order to understand to which socket channel this key relates. So for example, key provides a method channel, which returns me a selectable channel. That's fine. But this will be basically the same socket channel as here. So we will be able to easily use our connections map, get a particular processor. In Reactor, this is another abstraction around that, call it sync, not sync, but sync. And using this sync, we are going to say, give me a flux. The first one is related to reads, right? So I'm going to use the first one, and I'm going to say, okay, I want to supply this key to my flux. So far, so good. Anything is clear? A little bit complex? Yep.
So when you use the uncompleted method from your processor class, you unsubscribe all the blocks.
Say it again. So the question is when I have to use or
when you use your processor
yep.
method uncomplete.
Yep.
All the blocks unsubscribe. Because you have notified.
Yep.
Prior notifies and read notified.
Yep.
So there are flux.
Right.
When you use the incomplete method from your processor class, do you unsubscribe it all the flux?
Unsubscribe?
Yes.
So basically, once I have sent an incomplete event, the subscription and the whole stream should be considered as canceled. And the subscription inside on the subscriber side should be considered as canceled. So it's basically the stream become unsubscribed, because incomplete and on error are terminal operations or terminal signals. So once those signals appears, I can clean up everything related to the stream and say, okay, I'm done, because there won't be any more data, so I can stop listening to them. So basically it's unsubscription, right? Or signal to my subscriber that there is no data anymore. Yep, yeah. I answered, great. So once I have my selection, yep, way to supply my read notification, I'm going to use the same business logic in order to send write notifications. Here I'm using some data structure called a tuple. So it's basically a tuple, which is basically a combination, like one key and another key. It's under the hood an array of objects, which allows me to store everything in one hash map, like associate everything with one select socket channel without creating additional hash maps. This is basically for simplicity. And here I use read notifiers and write notifiers. Basically, that's it. Here I'm applying my connection handler. So I supply my connection to my client side, to my business logic, which is hidden there. So it's basically, once I call connection handler apply, I receive this connection here and will be able to build some business logic on top of my flux of byte buffers. And this is it. In addition, to run my application on some specific thread, because it's important to not just to run my business logic on some other thread and allows my main thread to do other things. This is important one. I'm using Reactor API subscribe on, which basically run this code on specified scheduler. Scheduler is abstraction around executors or thread pools. So now let's try to run this logic. I'm saying let's try because everything could go in the wrong way. You know, this is demo. And yeah, it started. And let me now, not here, let me just open. Yeah, it works. Hello, everyone from Reactive Server Engine. And here we go, it works, great. So I can open a few more connections, of course. It works, it works, it works, and it works, amazing. And now the main challenge is to figure out whether it's better than blocking I/O, because that was the main idea. The main idea of our presentation, to figure out whether non-blocking I/O and reactive non-blocking I/O is capable to solve 10K problem. So I'm using the same code, I'm using the same doser, I'm running the same socket server, and as you can see, it handled really quickly 10,000 of connections. It works. Yeah, my CPU is really working, so you will see that it become a little bit warmer. And if I'm gonna open my monitor, you will see that there is, yeah, as you can see, like my computer becomes warmer and warmer, which basically means that there is some business logic. And as you can see, all the CPU power is supplied for my Java process. But now we have to figure out how many processors are busy by my data handling. Basically, I have to say that I'm using thread pool in order to do my DOS attack. So basically, a few of threads will be, and few of processors will be busy by sending some hello DOS attack messages and read them back from the server. But in general, the most busy one will be only this, because I have only one thread, right? Anyways, this one thread is capable to process. Let me hide this and let me go back to. Because this guy is capable to process data as there is nothing in behind, and I'm able to open more and more connection without any problems. Do you see that? And it works with lower latency, and only one processor is busy. Only one thread processing everything. This is amazing. So what we have done by this time, we basically created Node.js server. That's what we have done, using more beautiful and reactive API. So let's do a quick summary. Come on. First of all, in order to start our connection, we have, like, in order to start reading, we have to wait for subscribe event. It's important. And since we in Reactive Stream world, everything start working only when someone subscribed. So we have to wait for unsubscribe event first. Then here we are using generate in order to drain data from channel, because we don't know how many bytes will be sent from the client to server. So we are going to create another flux, and we will concave this flux into the main stream, but this flux will easily allows us to drain data from socket channel until we get to the end, right? And this is cool because this is built-in feature in Reactor. Then we are using some, in one case, this is synchronous sync in generate. Another way, it's another flux sync, but this is basically a way to supply data, manually supply data to your publisher. And afterwards, we're using base subscriber, which is a convenient way to create subscriber in Reactive Streams without any problem. Project Reactor handles all corner cases for you, so you just need to write your hooks and process your data. That's all you need to know so far. But now we have to implement multi-threading. So now I'm going to show you how you can do that. An implementation of multi-threading data processing is really easy, believe me. So all you need to do, everything you need to do, you have to put only one operator here, publish on. And you have to provide a scheduler. You basically have to specify on which thread pool all of your data should be handled. And basically, all of those events will be rescheduled to another thread. And after this operator, everything will be run on specific worker inside this thread pool. Yeah, basically, this thread pool provides you a kind of a fixed number of worker. The number of worker will be equivalent to number of processors on your machine. But anyways, you will be able to run some data processing on one of those of them. I'm going to use, instead of using some some static one or singleton one, I'm going to choose only one worker. I'm going to associate a specific worker from this pool in order to avoid kind of running my task on a different one. I want to associate only one worker with this connection. So I'm using some wrapper scheduler single, which takes only one worker from the pool, and this worker will be dedicated to handling all notifications and kind of draining data from this socket channel, right? And now I'm going to use this scheduler here, and I'm going to use the same scheduler here because we have two source of notification, one about read notifications and another about write notifications. Both of them have to be handled on the same thread. This is important one. So I have to say that those notifications should be executed on the same scheduler as well, and that's it. That's all I have to do in order to run my application on a different, on specific worker and make my Reactive Server engine multi-threaded. And yeah, let's just simply put a breakpoint here, and I'm going to ensure you that now everything is multi-threaded. Or easily, I'm going to put some log message. So if you want to log something in your Reactive stream, all you have to do, yeah, let's do that here. All you have to do is to say, okay, log. Don't try to debug Reactive streams. This is a hard challenge. Instead, log everything, and this will make your life much simpler. And byte buff. Yep, here we go. Yep, I'm logging everything, and now let me, come on, let me stop this guy. Yeah, this guy stopped. Now let me run it. So here we go. I started my application. I'm gonna go to my telnet. And now, as you can see, everything is handled. Where is that? Yeah, parallel 1. Do you see that? The worker which is responsible for data processing is parallel 1. Now I'm opening another, sending some data. And now you can see that this is parallel 2. So I'm processing my two connections on two different threads. And since I have like 16 threads, they will be shared between all of my connections. So if I'm going to run my docker here, you will see tons of different different workers that process all of my connections. And all of them are shared between those connections to make my data processing much more efficient. All right.
Sorry.
Yep.
So that means he only going to create a new thread if the rest are basic.
No.
For each one.
No. I'm using the thread pool, so there is only 16 workers. And as in the previous example, as you may notice, I was using only one thread to process everything, right? So in the same way, I can use 4 threads and dedicate the same number of work, the same number of connection, but for 4 threads. And 4 threads will be shared and will share, for example, X number of connection between them. So instead of using only one thread to process all of connections, I'm going to use, for example, 4 threads, which makes much more efficient my data processing, because I'm not using only one core, but I'm using, for example, 4 cores.
So that was the. So you assign the quantity of threads you want to work with, right?
Yep.
So if I want to do that dynamically, I want to, like I don't want to say 4, but it depends on the capacity of the server.
So the question is, can I create, for example, can I create my own executor or my own thread pool or scheduler, which has for example, different number of threads in there, right? Or yeah, you can easily do that. For example, Project Reactor provides you with an API. This one is singleton one, so it's common or shared. You can easily create, for example, another one using the same schedulers. So there is schedulers API, and there is a few more methods in there. So you can create a single scheduler, kind of a scheduler with only one worker. And you can create your own, for example, parallel, and you can specify, for example, I want 15 workers inside it. And you can say, okay, this is my scheduler. And that's all you have to do. Of course, you have to provide some thread factory. Yeah, it's basically thread new, and that's it. You just created your new scheduler here, which has a capacity of 50 threads or 50 workers, and you can use this scheduler in there as well for your data processing. Yep, does it make sense?
Yeah. So, so if you have this like a 50 thread, right?
Yep.
So you use the browser is like generating all this data.
Yep.
So he's gonna be switching between every thread.
Yep.
As everyone get like a free or end of the process, right?
Say it again.
So they said that all the threads are busy.
Yep. Every thread will be busy because inside there is some round-robin business logic. So every new connection will be get the next worker from the pool.
Yeah.
So every worker will have, in general, the same number of work to do.
Okay.
It's like a load balancer.
Yeah, there is like inside new parallel, inside scheduler, there is a plain business logic. So once you want to have a worker, it has kind of an index, a common index inside it. So let me check it, and it will take. It start peak. Yeah, there is a peak. So there is round robin. So there is an index. So someone call it this guy, the index will be increased, and that's it. So the logic is pretty simple. So just a counter which will go to some point and return to 0, and again and to 0. So everyone. Yeah. Yeah, you can easily create your own scheduler and supply different logic of work sharing.
Two connections for one worker.
Yeah, you wanna reach like whatever you want. All right, let's move forward.
If I remember correctly, Nokia has this small problem that they only have one thread from the other, and basically you're doing it parallel. Probably there's 2 lanes of code, right?
Yep.
And I think probably that is happening because of the logic to make it work, like this kind of difficult logic to make the threads work with kind of contention or something like that, is because it's handled by the reactive.
Right, because Reactor is a kind of superset library on top of Reactive Streams. Since Reactive Streams is non-blocking asynchronous streams.
Yeah, and also there was some people who were doing at the start of the presentation that there is some way to get like the number of processors that Lightning has. So it basically decides based on the size of the server how many threads.
Yeah, by default, by default. Yeah, by default, if you're going to look at parallel, you will see that yeah, it creates parallel. There is a handler, default pool size. So it could be specified by some property. So you can set up the singleton one number of threads. And it fallbacks to runtime and available number of processors. Yeah, that's easy. All right, let's move forward. Any other questions? You will be able to ask them afterwards. Don't worry. So as you have seen, we can how easy it's to create the multi-thread and data processing without changing too much logic, because everything is built into Reactor. That's amazing. All right, let's do some more summary points, notable points. What you have to remember about multi-threading is that everything in Reactor is built on top, like around schedulers. So schedulers is basically a representation of your pool of workers. For example, parallel is a singleton one, which provides you as many threads as you have a course inside your computer. So it basically allows you to use publish on, which is one of the operators which will schedule events from one thread to another. And then you will get this connection, and you will attach your particular one of the workers from this pool to this connection. And what is important, since we are in non-blocking asynchronous world, the same worker will be able to process much more connections. Not only one, but much more. This is cool. This one allows you to take a particular worker from this pool and use it specifically for this connection. That's easy. All right. We just completed implementation of our reactive server using Reactor. As you have seen, there is some complex point, but in general, reactive programming simplifies the implementation. And the user experience, which is basically, and the user basically gets this API, is much more better. So you will be able to process your data in a much better way. We have seen that it's really easy to implement multi-threading and schedule data processing on some specific worker from the pool. But now the question is, where is back pressure there, right? I've been talking at the very beginning that back pressure is an important point, and I have shown this demo with back pressure and data sending. So where is back pressure, right? So in order to answer, I created another test. That basically shows you back pressure. So now I have to modify my data processing a little bit. First of all, just imagine that your producer is really fast producer, like this one. So let me open my test first. Here's my test. And here is really fast producer. So I'm using the same blocking socket channel in order to simplify my life, because imperative is still better. And I'm using just while true loop in order to send the same hello DOS attack. So now a different problem. I'm just sending data, sending data. And I can overflow my server with those data, right? Now we have to figure out whether our reactive server is capable to apply back pressure, because this is reactive streams, so it should work out of the box. And my producer here, my consumer here, because this is a server side, could be really slow one. So I'm gonna use another API from Reactor. So I'm gonna use concate map. I'm gonna create monoadjust. I'm just using the same data here. And I'm gonna delay my element for some specific period of time. So my producer produces data every nanosecond, I would say, really fast. But my consumer consumes those data with some delay, right? And concate map will make sure that only one element is processed at the point in time. So now I'm going to run the server. This is my server. Yep. Let's do a little bit different thing. I don't want to send anything back. I just want to keep mono never byte buffer I don't want to send anything back, so I just want to read data from connection. And yeah, I'm going to run this guy. So it's running. And now I'm going to start this guy again. And it should, let's run. What's wrong with you, buddy? Okay, it's running. As you have seen, I have a counter there. I've sent 51,000 and something messages, but it stopped. At the same time, this guy is reading something. With some delay, it's reading messages, which is good for us. And this guy, yeah, back pressure works, but in some weird way. Do you see? We got some few more messages. We got one by one. At some period of time, we just sent only one, and then we sent much more of them. So in general, back pressure works. As you can see, my producer stopped at some point in time because my consumer is really slow. But the behavior is a little bit unclear. Why my producer produced too much messages? Even so, I requested, for example, a few, only one or only two. This is the main question because, yes, you can see I produced another 20,000 of messages. So do you have any ideas? I'm going to give you an answer to that question. To that question. First of all, in this, yep.
Not all of us like busy at the same time waiting for an amount of time, so they are like doing it like.
No, my connection is processed only by one thread. Only one consumer is consuming data. So yeah, I'm going to show you that. Yeah, here we go. Only one parallel thread is reading all the data. The problem is in TCP and in the way how we handle this back pressure. Since we are using TCP under the hood, and we are using socket channel. And socket channel does not have this way to request some data. There is some way, like if you're going to Google for TCP flow control, you will find out that TCP works, data sending on TCP works over the windowing. So TCP itself implements some back pressure. So until the server send an acknowledgement, the client won't produce anything. So this is the way how back pressure works in TCP. So there is a window, there is some window size, and this size is measured in bytes. So it could be 65,000 of bytes. And like the window size could be 65,000 of bytes. But this makes, like it gives enough space to send a little bit more data, right? So if you're going to look at how it works, like I found a pretty good video animation which explains how TCP byte transmission works. Basically, there is a window on the server and client side. Server client can send few more bytes. In our case, it's 50,000. Anyways, and then client would have to supply them, and only after that, the server will send an acknowledgement that I processed those 3 bytes or many bytes. And only after that, our client will supply a little bit more data. But again, this is much more than we requested, in fact, because we are reading a little bit more there and we are writing a little bit more here. Everything is buffered on the network card and so forth and so on. So in general, back pressure works in this way, in the TCP way, but this is not real, real back pressure. It works, but
one client, right? Like if there were, I don't know, 1,000 clients or 1,000 different IPs, that back pressure is going to work.
Exactly. Like this back pressure won't be able to, like, it won't be kind of scale it or share it between everyone. Thank you. So in any case, it's possible to overwhelm of a server. And this could happen with your gRPC, because gRPC works on top of HTTP2, and HTTP2 has basically the same windowing. And gRPC does not provide any real backpressure support. So to summarize what we have seen, Neo API is still complex, but Reactive Streams simplifies it a lot. Reactive Stream brings backpressure support. On top of TCP, it works, but not really well. Project Reactor simplifies logic because we have this fluent API with map, reduce, filter, concate map, etc. And this is non-blocking asynchronous way to process your data stream. And it brings multi-threading out of the box. This is cool. So what we have seen the smallest part of Netty. Have you ever heard about Netty before? Okay, just a few hands. So Netty, this is Reactive Engine. This is basically an implementation, a little bit more smarter implementation on top of non-blocking I/O, the same non-blocking I/O, but now you know how it works and what challenges and what problems is hidden inside non-blocking I/O, the first version of non-blocking I/O. In general, Netty is the same complex, but what is the good news is there is a wrapper around Netty, which is called Reactor Netty. So you can easily get the same API, you can easily get the same power of non-blocking I/O with built-in or superset reactor, Project Reactor on top of that. This is cool. If you want to achieve real backpressure, there is our socket project, which is basically the same Reactive Streams, but over the network. So it's a Reactive Streams protocol. So you can take your one flags. Under the hood, there is Project Reactor. So everything could be transmitted over TCP or over WebSocket, but our socket is a protocol. It's not a particular wrapper on top of HTTP2 or TCP. It's a protocol which brings you Reactive Streams kind of signals as frames, as byte frames, which allows us to transmit backpressure in a proper way. And finally, to learn a little bit more about reactive world, because it's really complex, to learn a little bit more about Neo, pure Neo, I recommend you to take a look at the first video. This video inspired me at some point in time, this video from Hein Kabutz, which basically creates almost similar Neo server, but he shows how to do that without Reactive Streams. So if you want to recap how Neo works, please take a look at this video. If you want to learn a little bit more about Reactor, there is an amazing documentation on the official website, so you're welcome. And nowadays, Reactor could be used on Android because Android started supporting Java 8. And there is Reactor for JavaScript as well. So you can get the same benefits in JS, in Android, and in Java. If you want to learn a little bit more about TCP flow control, please take a look here. And if you want to look at Reactive Streams as a network protocol, welcome to our socket IO. This is basically it. Thank you for your attention. Really, thank you. This was really complex talk. And presentation is here. The source code is there. I'm leaving here, so please follow me if you want to ask few more questions. Thank you. Any questions?
So I have a question.
Yep.
So all of this is explained. Yeah, I give you that. It's complex.
Yep.
But the main reason to implement Reactive Programming on the server would be to make the request or the server more efficient. Because you can do it like you have explained it how to do it programmatically. Because for instance, if you know AWS,
yep,
let's say, you could use that to make the requests more efficient, but it's going to cost money.
Yep.
But that you can like do the programmatically and use them like both together. That's
yep.
what the requirements money.
Yep. So basically, what I try to explain is, first of all, blocking is expensive. Threads is really expensive. So what you have to try is you have to try to avoid blocking I/O, blocking communication, because it's, again, money-wise. You will be able to handle much more connections on the same machine. And of course, you can scale your application. You can scale your system, but again, you will spend much more money. And if it's important for your company to decrease number of spends on your infrastructure, on your, for example, AWS environment, then it worth to try. On the other hand, I tried to show that non-blocking I/O, like core non-blocking I/O, is really complex. It's not easy task to start working with non-blocking I/O. And
basically, you have to understand TCP.
Yeah.
And you have to know network programming.
Right. Yes, and this is a problem. And Reactive API makes this kind of challenge and work much simpler because it brings paradigm of reactive streams. So only things that you have to work with is just a flux of byte buffs. You don't have to challenge your colleagues and yourself on working with this lower stuff. And everyone will be able just to do something like this, to write some filter, maps, and other fancy operators. That's all they have to do. And this is much better. And it brings asynchronous non-blocking way to process everything. And the final point that I tried to show is that the TCP itself has some other way of handling back pressure. So you have to remember about them. And once you start, for example, sending your stream from one client to another, you have to remember that under the hood TCP has its own windowing, and there is a little bit another back pressure paradigm. So you have to bear that in mind.
Talking about the OSI model.
Huh?
OSI model.
iOS or
Yeah.
OSI
model. OSI.
Yeah, like do you mean like these layers of? Yeah.
That's what you mean.
Yeah.
Okay.
But this is not for, like, there is application level, but this is TCP is lower layer.
Yeah.
We've been talking about this transport layer.
That's level 3 or 4.
This is level 6 as far as I remember. The 7.1 is application, the 6.1 is transport. So we've been talking about transport layer. Any other questions?
So you're using ReactiveManifesto like a protocol to handle back pressure over the wire, right?
Yeah, it's a transparent way to send your one reactive stream to another service.
So have you, I don't know, probably you're like encapsulating some data if you're doing from HTTP or something like that? Or how are you using ReactiveManifesto?
Like, basically, it provides you, like, what you have to do, you have to take, for example, your logical data. You have to transform this logical data into byte representation. But the benefit is that this message will be taken and considered as one logical message, will be transmitted over the network, and then you'll be able to decode it back as one message without doing anything on the receiver side.
So the signaling for back pressure?
Yes, with signaling back pressure is basically a frame. Like if you say, okay, request N, and you call this request N here in this way, like here, you can request 1, you can request 10, you can request 100. This method invocation will be transformed into binary frame. You'll be transmitted over the network, and then the receiver will transform this frame into the same call on the receiver side. And yeah, this is basically a superset on top of reactive streams and on top of transport, which basically simplifies your life in case you want to work with this style. Yeah, in general, reactive streams is a change of mindset because you don't have any imperative code. Like you have it, but you have to work with it in a little bit different way, in a functional way.
It's similar to the actual model, basically. Like concept, moving order, but you know that it's really good to see it in Java.
Yep.
Like that. So all those kind of things.
All right. If you don't have any more questions, Noel, please finalize this evening.
Yeah.
It was tough, like lots of information. Yeah, but first of all, thank you for your attention. It was cool.
No, first of all, thank you for coming to
My
Santo
pleasure.
Domingo.
My pleasure.
Muchas gracias. Nada, gente. Agradecer a Oleh por su participación. Tiene un viaje aquí a la ciudad. Tenemos un par de anuncios que menciona, pero principalmente gracias también a Point que nos prestó el lugar. Point también está buscando alguna gente interesada o que estén cuidando con Kotlin. Si lo conocen a alguien, a team@point.deo pueden mandar por referir ese correo para Edwin va a presentar un par de cosas. Después de eso tenemos un compartir, unos picapollos que traímos.
Apoyo de harina.
Picapollo de harina.
Eso lo vino en otro país, tú lo hablas de picapollo.
Ay, no, pero eso aquí a ustedes.
A tú le vas a dar.
No, a él le llamo como friquitaki.
I can just assume what we're saying.
No, we're joking about food. We're just joking about food.
Okay.
I guess while we are waiting for something, I would love to have a selfie with you all, guys. So please do that.
Oh, Cedric.
Hey, selfie.
Yeah, selfie, everyone. Is it? Yep. Hey,
Hey.
thank you. Great.
Okay,
Thank you.
bien, ya, thank you so much to Oleh. Entonces, para concluir, hacer algunos anuncios, recordarles, tenemos algunos grupos de estudio, dale a la flechita, el teclado. Okay. Algunos grupos de estudio que están ahí en el enlace, están en nuestro Instagram, en nuestro Meetup, en Facebook, donde quiera, usted busca GDG Santo Domingo, está Study Group de Kotlin, sigue. Para Flutter, sigue. Y Cloud. Entonces, estamos esperando, dale para atrás, acuerdo. Bueno, estamos esperando que se inscriban más personas para nosotros entonces comenzar a trabajar en encontrar un lugar y la logística y demás, ¿verdad? Para empezar con el estudio. Sí.
Disculpa.
Ajá.
¿Para qué nivel están pensando?
No, o sea, los study groups está pensado para gente que quiera aprender, o sea, que no lo sepa. Que tú no sepas nada de Kotlin, de Flutter, y que tú quieras dar los primeros pasos. Esa es la idea del study group. Ojo, el que ya sabe, no se limite porque o sea, el study group es una, digamos, una mini comunidad. O sea, si tú sabes algo, tú quizás puedas aportarle al maestro que lo vaya a impartir o lo que sea. O sea, que es un asunto de ayuda mutua y del espíritu comunitario.
Quizás aprender un poco más. La idea es, hay un contenido preparado semanal, como un currículum, pero muy serio. La idea es que en esa persona se provee el contenido cada semana que se comunica. O sea, independientemente, hay gente que aprende cosas que no están en el contenido o que vale la pena mencionar.
Exacto.
Y la idea es compartir, hacerlo con nosotros.
Exacto. Sigue. Miren, esto tenemos un anuncio bien interesante que hacerles. En el próximo septiembre, nosotros vamos a tener el evento más... primicia. El evento más grande de tecnología Google, que pueden organizar los Google Developer Groups, que es el DevFest, pues vamos a tenerlo junto con otro evento que les voy a mostrar luego. Vamos a tenerlo 20 y 21 de septiembre. I talked to Oleh already he said that he wants to come to DevFest. So it's next September 20 and 21.
Okay.
Yeah, DevFest and the other event. So let's see. El otro evento es Kotlin Everywhere. Ese día son 2 días. Me parece que es viernes 20 y sábado 21. Entonces, el día de Kotlin Everywhere, todo es sobre Kotlin. Para que sepan, Kotlin no solamente es en Android. Entonces vamos a tener charlas de Kotlin en backend. Kotlin se puso en lo que sea. Es decir, vamos a ver si conseguimos alguien que hable de Kotlin en iOS. Hay muchísimas aplicaciones. Entonces vamos a estar hablando de eso. Dale. Estos son, les pueden tirar fotos, si quieren hablar, si conocen a alguien que quiera dar una charla de lo que sea, tanto para el DevFest como para el Kotlin Everywhere, pueden enviarle estos enlaces en PaperCode, ahí submitean su charla. Oleh, we have a PaperCode already, so if you want to submit, you can go ahead and do it right away. So, entonces, sigue. Bien, también queremos anunciarle este evento, no tiene que ver con nosotros, pero sí es un evento que se va a estar realizando el próximo 10 de agosto. Yo personalmente estoy colaborando, me pidieron pues ayuda en cuanto a algunas cosas ahí y según lo que he podido ver va a ser un evento bien interesante. Le pueden dar seguimiento, me dijeron que ya hoy iban a estar creando todo el asunto en las redes sociales. Es un evento totalmente
fuera de alguna tecnología X, o sea que va a ser muy abierto, va a tener de todo un poco, y pues les invitamos a que participen. Vale. Esto es todo, pueden seguirnos en las redes sociales, en todas esas que están ahí, lo buscan por GDG Santo Domingo, y seguro que nos encuentran. Por ahí vamos a estar publicando siempre los meetups como este.
Hay un plan de meetup, ¿no?
Sí, en este mes, o sea, yo les sugiero que estén activos con esas redes, porque siempre en este mes vamos a organizar, de hecho con Raymond, que se encuentra aquí, vamos a estar organizando algo de Angular y así, o sea, vamos a estar bien activos. De aquí, sobre todo por el DevFest, pero en general vamos a estar bien activos y nos pueden seguir por ahí. Nuestra plataforma oficial de hacer este tipo de cosas es Meetup, entonces nos buscan ahí, se pueden unir a la comunidad GDG Santo Domingo. Bien, pues muchas gracias a todos por acompañarnos hoy y nos vemos en una próxima oportunidad. Y no se vayan sin comerse un muro de pollo. Sí, un muro de pollo que tienen hoy.
Uno solo.
Gracias.